So in the next videos, I would like to discuss some transistor configurations. And in fact, it's good to know what kind of transistor you're dealing with because it can help you and make the problem solving much easier because there are certain formulas and equivalents for each transistor, but of course the basic relationships are always the same. So today I'm gonna discuss voltage divider bias configuration as well as solve a problem on it. So when it comes to this specific configuration, you want to consider the left part with the source voltage, resistor 1, resistor 2, separately from the RC, RE, and base, as if you are shutting off the transistor, okay? So this is called a Thevenin equivalent, and according to it, you can replace whatever you have on the left side of the terminal by an equivalent. So we start off by calculating the equivalent for R1 and R2, and for that we are gonna take VCC equal to 0. So we kind of shut off our source voltage, and you might wonder, why are we allowed to do that? This is because we are essentially calculating the internal resistance of our circuit, and an ideal voltage source has to actually maintain a fixed voltage regardless of whatever current is flowing through it. So its internal resistance in that case is 0. So if we want to see the internal resistance of the circuit, therefore in an ideal case, the resistance of our voltage will not contribute, and thus we make it, from a calculation standpoint, equal to 0. So essentially, if we consider only the left side, we have something like this. So this is our R1, this is our VCC, sorry, it should be like this. This is our R2. And this is the rest of the circuit with a transistor, okay? So if we are looking from this side to make an equivalent, and as we said, we're turning off the voltage source, this thing becomes just grounded like that. And this thing becomes grounded as well. So essentially, we're saying that the Thevenin equivalent is equal to resistor 1 and resistor 2 in parallel. So the second thing is we have to calculate the Thevenin equivalent voltage, and we call it ETH. Okay? And for this one, we have to ask ourselves, so if nothing is connected to the left side of a circuit, meaning that the base, collector, and emitter are not connected, then is there still some voltage? So is voltage present? In order to do that, we're making an assumption that IB is equal to 0, which is quite obvious. And now it becomes clear that if there is no current leaving through the base, then the base voltage is just the voltage divider output, right? And in this case, it coincides with the voltage across the resistor 2. So our ETH simply becomes VCC multiplied by R2, R1 plus R2, according to the voltage divider formula. So now that we draw the equivalent, there is a voltage, Thevenin voltage equivalent, Thevenin resistor equivalent, our normal base, collector, and emitter. Okay, and here comes the current that flows through the base, our VBE. And this is the circuit that you may solve, and it's much easier, right? Because now we can say that ETH minus RTH multiplied by IB minus VBE minus RE multiplied by IE is equal to 0. So IB is equal to ETH minus VBE over RTH plus RE B plus 1. And from knowing what is IB equal to, you can find what is IE and IC is equal to. Now VCE, the last unknown component, will be equal to simply VCC minus IC multiplied by RC plus RE. And that's it from with the theory. So now that we know all the formulas, we can solve an example on our configuration. So here we have to find what is IC and VCE equal to. Let's first draw the equivalent of the circuit. So we will have ETH plus minus connected to the ground, RTH, B and our transistor, so RTH is equal to R1 in parallel with R2. In that case, it will be 3.9 kilo ohms multiplied by 39 kilo ohms over their sum. So this is equal to approximately 3.54 kilo ohms. Now the Thevenin equivalent will be equal to VCC multiplied by R1 plus R2. You can calculate yourself, it's very easy, so it will be just 2 volts. Next, we have to calculate the base current. If we use the formula that we derived previously, it will be equal to ETH minus VBE over RTH plus RE B plus 1. So here, if you calculate it, you will get 838 microamperes. So now that we know IB, we can calculate IC, which will be equal to beta multiplied by IB. And this is just 100 multiplied by this value. So this will be equal to 0.838 milliamperes. And IE will be something near that value. In fact, it will be 0.47 milliamperes. I know that we roughly approximate IC and IE, but in case if some of your professors are very strict about the values and the approximations and the approximation up to subdecimal, I highly suggest you to use this specific accurate formulas, because you are risking to lose some points, okay? This is what usually happens to me, so don't repeat my mistakes. So now we have to find VCE, and I didn't show how we derive VCE. So basically we just look at the collector emitter loop over here, and from that we can say that VCC minus IC RC minus VCE minus IE RE is equal to 0. Okay, so we're taking into account everything over here. So our VCE will be equal to VCC minus RC IC minus IE RE. And this will give us 12.35 volts. So with that, I'd like to conclude. Thank you for watching.